Então, eu gostaria de apresentar o palestrante da nossa aula magna. É um prazer ter o professor Carlos Graeff para ministrar essa aula para a gente. O professor Graeff é professor no Departamento de Física da Faculdade de Ciências de Bauru, da própria UNESP. Ele é atualmente o nosso pró-reitor de pesquisa até o final do ano, né? Até o final do ano, então, da gestão atual. O professor Graeff fez a graduação, mestrado e doutorado na Unicamp. Somos colegas, então. Ele passou um tempo em diferentes, foi professor visitante de diferentes universidades, no EPFL em Lausanne, na Universidade Técnica de Munique, entre outras. Ele é membro da Academia Paulista de Ciências, ele foi membro do CA do CNPq, e ele recentemente começou uma nova empreitada no Instituto de Inteligência Artificial, que é algo bastante interessante, está bastante na moda. Então, ele vai falar um pouquinho para a gente sobre a pesquisa dele em células solares, e eu vou passar aqui, então, a palavra para o professor Graeff.
Então, in English, huh? Yep. So, thank you very much. It's really a honor and a pleasure to give this first lecture. Oops, melhor desligar. So it's okay. Tá dando aqui retorno. It's a great pleasure to be here. The first time I heard about IFT, actually, I was just joining CAPS as a vice coordinator for materials, and then Jairton Dupont came to me. He was the coordinator of the chemistry, and he told me, do you know which is the best physics postgraduate course in Brazil? And I said, well, I'm not sure, maybe USP, maybe. No, he said, it's from your university, it's the IFT. I have all the numbers here. The IFT is the best postgraduate course in Brazil. So this was my first impression from IFT, and so I would like to again say that it's an honor to be here. So what I'm going to talk about is one of the topics that we develop in my lab. So I'm an experimental physicist, and this is on solar cells. And actually, this is the subject that I've been pursuing since my graduate course. So when I started doing master's and PhD, I did it in the photovoltaics group in Campinas with Chamboleron. So the main challenge that we are facing, as you know very well, is that we need energy, and basically the most important source of energy nowadays is based on fossil fuels, and deixa eu ver aqui. Oops. And basically, I'm trying to use this, but basically the problem is that these fossil fuels, they produce CO2, and CO2 is responsible for all this climate change, which is more and more evident as the years pass by. So if you look at the consumption of energy around the world, it's clear that in some places, basically, we don't have any more problems of feeding more energy. But in others, like in Africa, there is clearly demand. So the demand for energy is growing. And if we keep on using just fossil fuels, we are running into real problems. This is more or less the growth in primary energy consumption from the 50s to 2020. And as you can see, it's really ramp up. And basically, the blue is oil and biofuels. And here is natural gas. So you see that these are mainly coming from, and here is coal. So these are all producing CO2. So we have a demand for finding energy sources that are renewable, that don't produce CO2. And here is more or less the statistics in 2017. Only about 5% of the energy produced in the world is coming from really renewable sources. So solar, wind, geothermal, and tidal, okay? And basically, this is the distribution of these renewable energies along the years. As you can see from 2010, the projection to 2040 is that this will be growing steadily in the next few years. And basically, as you can see here, nowadays, the main source of renewable energies is hydropower, but it's declining along the years. And this is clear, as I will be showing in the next few slides. So the question is, if we are going to use renewable energies, how much of this energy is available? And if we use this graph and as a parameter, for example, hydrothermal is basically the amount of energy available in the world today is the amount of energy that we need. And since it's growing, of course, that hydro energy won't be the source of renewable energy in the future, because basically there is not enough sources to feed us. But on the other side, if we go to wind, we have 200 times, in principle, energy available to convert. So even if we grow the amount of energy needed, we have 200 times, so we can use wind without any restriction. And if you look at this big one, which is the solar energy, it's about 3,000 times the energy, all the energy the world uses today. So it's basically a source of energy without any border, so we can use it as much as we want, okay? And this is more or less how the global solar energy generation is growing along the few years, so 1990s until 2016. And one interesting point, you see that in 1990, if we take all the energy produced by solar cells in the world, the United States were responsible for about 96% of all the solar photovoltaic energy produced. Nowadays, China is the leading. It's 20%, in the United States 17%, Japan 14%, and Germany 15%. So there is a clear change in the production of solar energy, and it's basically the main source is China. China is basically 99% of the solar cells produced today are produced in China. So China is dominating completely the market. So if we used 1% of the covered area in the world with 25% efficiency, we would produce 0.5 billion terawatts. Just to give an idea, because people say, well, okay, I can use solar cells, but they need area, because they are basically panels, big, so will be enough area for me to use to produce. It's really ridiculous, the amount of covered area, and we can use the roofs of our buildings to produce it. So there is no restriction in this point of view. In Brazil, especially, as you can see from this graph, this is the irradiation in the whole country. And as you can see, it's especially good in places where there is no agriculture. If you're going to, it's going to compete with land for producing harvest. No. The best places are actually desert. So we have a big potential to produce solar energy. However, as you can see here, if we take only some sources of energy, you can see the hydroelectrics is 61%, thermoelectrics 20%, eolics 3%, solar energy is just 0.02%. It's basically the same as the nuclear power. So nowadays, solar energy has just passed the nuclear production of energy in Brazil. But anyway, Brazil is very green. Compared with other countries, we have 61% of hydroelectrics, and we can sum up 3% in wind, and we are quite okay. So I was talking about the whole energy use, and I'm sorry some slides are in Portuguese because I'm taking from another guy, and so it's in Portuguese. But the interesting thing is that the need of electric energy is growing. Okay, so when I'm talking about global energy, I'm talking about also the gasoline used in the cars, the alcohol here in Brazil used in the car. But the amount of energy, the percentage of energy that's becoming electric is growing year by year, and nowadays it's more or less 45%. And then thinking about that, solar energy is even better because it's one of the most efficient ways to convert light or energy into electricity, okay? And this is going to be especially true when we are changing from the cars that are based on combustion to electric cars. Then solar energy will be perfect. However, as everything, it's not perfect in the sense that it has its draws. And one of the drawbacks is this. If I am taking time, the real time, from midnight to midnight again, this is a day, okay? And I'm talking about aeolic or wind, thermoelectrics, hydro, nuclear, and solar. And of course, we just have sun a part of the day. And it's changing, the amount of energy that is coming from the sun is changing, as you can see from here, along the day. So the big challenge nowadays is how can we use these sources of energy that are not constant in a matrix that is based, you don't want in your house, oh, now I can switch this light on, and now I can't because there is not enough energy coming in. So I need something very stable. And in this sense, nuclear is the best. Nuclear energy is the best in what concerns how constant it is. But Brazil is really very special. As I told you, 61% of our energy coming from hydroelectrics. So we have a natural source of keeping renewable energy. So we can use solar energy during the day and switch on our hydroelectrics during the night, and water will be the way to keep energy. So we don't need supercapacitors, we don't need any special, or batteries, super batteries. We can, in Brazil, if we are smart enough, use our matrix to have, we can, in principle, be fully renewable. Brazil has this chance. It's something very special here. Okay, so what are solar cells? As I told you, solar cells are these big panels that nowadays, as the technology is developing, we can actually have it in many other forms, okay? So you can have it on the roof of cars and everything like that. And actually, there are a myriad of technologies being developed to this challenge. And here is a compilation of all the solar cells available today and their efficiency. The efficiency is the amount of the conversion. So if there is 1 watt coming in terms of light, of solar power coming in, and I have 10%, I will have 0.1 watts in electricity, okay? And so as you can see, there are cells that can reach up to 47%. So half of the energy that's coming in a way of light is converted into electricity. These are very special and very expensive solar cells. There are the most common ones that you can buy on any shop are these crystalline silicons, are these blue. And the records are more or less about 20%. But if you go to a shop, you buy, you get it, if you are lucky, 10%, 8%, because of course these are like very small cells, very special, done in a very special way. So the ones that you buy in the shop is typically 10%. What I'm putting some evidence is on this new technology that appeared in EPFL, so by coincidence, the place that I was visiting professor, in about 2013, and suddenly it came from about 14% to about 25% in a few years. Very, quick development. And these are the perovskites. So this is why there is really a huge interest in the community on these perovskite solar cells. And this is a little bit that I'm going to talk. That is the technology that we are developing in our lab. But before going to that, just to give you the general idea, how can I convert light into electricity? For that, what we need is a semiconductor. A semiconductor is a material which has what we call a band gap. If you put the electrons inside this material, it will fill up one of these energy bands, and the upper level, which would be available for the electrons, is basically empty. So you have what we call an energy gap. What happens is that as you shine light, okay, you can absorb by the transition of this electron from this low, which is called the valence band, to the conduction band, or if you are talking about organic materials or molecular materials, it's from the HOMO, highest occupied, to the lowest unoccupied molecular orbital, okay? So you generate an electron-hole pair, okay? And then what happens is that you have to have some driving force for this pair. So I have an electron and I have a hole. One of the electrons must go to one contact and the hole to the other contact. Otherwise, I'm not generating no electricity. So I have to have some kind of driving force. This I can produce by many tricks. One of them is creating an internal electrical field. These are charged, so they will follow the field, and then one is positive, the other is negative. I will do the positive to one side and the negative to the other side, okay? And then I have to have selective contacts. These contacts must only accept the transfer of electrons, and this one only of holes. Because in the end effect, if this would receive an electron, it's like neutralizing the charge. So I'm putting a positive charge and a negative charge, it's zero. Then I have no conversion, okay? And so all these technologies are basically doing the same, but I have many tricks to have this working as perfectly as possible. So I have to have the maximum absorption of light, the maximum way that I separate the charges. Remember that they are opposite charges, so they have Coulomb attraction, so I have to find a way to detach one from the other, and I have to be sure that they transfer to these contacts the most efficient way. So this is basically the challenge for physicists, for engineers, and this is a little bit what I'm going to tell you in the following for the specific case of the perovskite solar cells. So the perovskite solar cells are basically this structure, and the name comes from the crystal structure. Perovskite is no material. Perovskite is the crystal structure. So the material is basically a hybrid material. So if you say perovskite to anyone, to a geologist, he will say, well, what are you talking about? You have perovskite of many, many other elements. This one is a very specific one. It's a hybrid material made of an organic and an inorganic part. The inorganic part is basically lead iodide, and this is methylammonium, okay? And they are structured more or less like this. So, as I told you just a little bit on the history of the perovskite solar cells came basically from one other technology that I didn't talk about, which were the so-called dye solar cells. And the idea is that if I have a nanoparticle of TiO2, and I have, for example, something here in the surface that absorbs light, I can have a solar cell working here. I won't go into too much details, but this is the first structure used to produce a perovskite solar cell. And rapidly, as I told you, there was one record after the other. One of the guys that was important for this is this guy here, Henry Snaith. But basically, there was quite a lot of development coming from South Korea. South Korea was a major player here. So just going a little bit more into details, why this perovskite, this lead iodide methylammonium is so interesting. One of the things is that it has what is called the perfect band gap. If one calculates what would be the best gap to have a single junction, what I thought, just one material, to convert light, sunlight, it has its spectrum, sunlight into electricity, the gap is about 1.5, exactly the gap from perovskite. It has a high absorption. As you can see here, comparing with silicon, this is the perovskite and this is GAS. You can see that silicon has a gap of 1.1, but it's what is called, if you study solid state physics, it's an indirect gap, so the absorption is not so good as with direct gap like like the perovskite or gallium arsenide. So that's why they are so steep. And this is the cell that we've been producing and studying in Bauru. So basically, it has many structures. As I told you, there is a lot of technology involved, of know-how to optimize this. And we have basically the following. We have a glass, and on the top of the glass, we have a transparent conductor, which in our case is FTO. And then we produce a layer, a compact layer of TiO2. This is a mesoporous structure of TiO2. The perovskite is here, and then we have what is called a hole transporting layer, one of these layers to make this extraction of the carriers, and here is gold, okay? And they look like this. This is a real cell. You see that it's black, which is good, because this is telling me that it's absorbing a lot of light. But actually, there are many different structures that I'm not going into details, but just to be honest with you, we have this with the mesoporous, which up to now is still the best, the most efficient cell in the world. But we can have without the mesoporous part, we can have it inverted. You see, here is the electron transporting layer, and here is the hole transporting layer. So you have many different structures. Actually, I just came from Germany. I was in Berlin. And the guys there in the Helmholtz-Zentrum were basically following all the papers in the world in perovskite. And the numbers are, it's published about 20 to 30 articles per day on this material, on this device. So the active layer, as I told you, is the perovskite. And as you can see here, actually, we can play around with many different combinations of materials, and these have effects on the crystal structure, on the gap, and everything else. Again, I'm not going to too much details. We have many materials that are used for the whole transporting layer, and the most common is pyrometad, but there is graphene. I know that there are people here working with graphene, fullerene, inorganics, okay? And electron transporting layer are also there are not so many options, but basically PCBM, TiO2, and what is new and that I'm going to talk about is the niobium oxide. So, as I told you, one can focus on any one of these layers and try to optimize, and this is enough. It's quite a lot of work to optimize any one of these layers. So TiO2, as I showed you, is quite an important part in the working of this device. And it actually has a problem with TiO2 because I didn't go into too much details, but these materials these solar cells are not as stable as silicon, so they have degradation. And the challenge of these 20 papers per day that I told you on perovskite is basically trying to solve this, to make them stable. And there is another effect which is called hysteresis, which I'm going to talk about, that we're trying to get rid of. And TiO2 may be a component that is responsible for the degradation of this material, because it's well known from the chemistry that TiO2 is very effective in photoreactions. So what we try to see is, what about removing TiO2 and introducing niobium oxide, which is very similar. And why niobium oxide? Here in Brazil, I don't have to talk too much because everybody remembers one politician that was the niobium. And so I don't have to tell you. But basically, in what concerns the production of niobium, Brazil is 90%. Doesn't mean that niobium is all here, but the mines, we export basically 90% of all the niobium. And this company, CBMM, is actually a very interesting company, and it finances research on niobium quite well. If we have time, I can talk a little bit about this. But from the point of view of the application that we are thinking about, it's quite interesting because it's very similar to TiO2, but with some advantages. Among them, it's that it's quite an efficient electron injector. And as I told you, this part has a very important effect in the injection of things. I'll come back to this later on. Of course, that as I told you, the community working with perovskites is basically huge around the world, and we are not alone. There are groups in China, in South Korea, trying to process and work with niobium oxide in different ways. There are different synthesis rules. Again, because of time, I'm not going to go into too much detail. I'm going to just talk a little bit about our work and try to illustrate what are the challenges for anyone, any of these technologies, how we can try to optimize things. So as I told you, the basic idea was to change this compact layer with niobium. And to produce niobium oxide, we use reactive sputtering. Okay? And this is the structure. It's basically the same that I told before. The HM is this pyrometad. Okay? The sputtering technique, for those who are not used to, is a technique for depositing thin films. And there are some nice and bad things about it. One of the nice things is that you can control the reaction very well, because basically the technique uses argon to bombard a niobium, in this case, niobium target. And these metals or the niobium is ejected. And if I have oxygen inside this vacuum chamber, there is a reaction and you produce this oxide. And you can control by the flux of oxygen and argon how much oxygen, for example, there is inside the film. Okay? So it's a very nice technique to produce very homogeneous films in the lab or in the industry. And here are the films. The films are really very nice. So they are very homogeneous. We can control very well the thicknesses. We are sure that we are producing niobium pentoxide by looking at the crystal of the diffractometer and things like this. The perovskite, the nice things about the perovskite, and that's why it has brought all this huge interest, is because it's basically so simple to make that even a child could make it. If you have a substrate and you drop either PBI and then MI solution and rotate, it basically forms the crystal automatically. You don't have to do anything. It produces. Okay? So that's why it's attracting so much interest. So the perovskites, they form not real single crystals. They are nanocrystals to microcrystals, depends on the parameters you produce. We can attest that by X-ray diffraction. And then finally, to finalize the structure, we deposit the spirometad and the gold. And here is basically, again, the solar cell I have already shown you. This is the cell from the side. So here is basically the glass with the FTO. Okay, so here glass, FTO. And then you have the mesoporous, the perovskite, the spirometad, and gold. And these layers are typically, as you can see, of 100 nanometers, 200 nanometers, are really, really very thin. We use a very, very little amount of material, very, very little. Now I can talk a little bit about one big advantage of niobium oxide that will be more clear in the next slides. As you can see, niobium is quite similar to titanium oxide, but it's not really equal, and especially in this, what is called the conduction band. It's a little bit, as you see, a little bit less in energy than TiO2, and this will be fundamental for what I'm going to explain in the next. So we did cells with the conventional technique, which is TiO2 compact, TiO2 mesoporous, and cells where the compact layer was changed to niobium oxide. I'm just worried with time who is controlling it. So okay, 15 minutes. Okay. So we changed TiO2 for niobium. And now I'm going to talk a little bit about this technology. So as you saw from the basic principles, working principle of a solar cell, you have electrons going to one contact and holes to the other contact. So this is basically a diode. If you analyze from the electrical point of view, it's a device where current can only flow in one direction. In the other direction, there is no flow. So this is a diode, a common diode that is used so much in electronics. And this is what we are seeing here. You see, if I have in reverse voltage, there is basically no current passing in this device. And as you put positive voltage, suddenly there is a point where there is a lot of current passing, and it's exponential, just like the diode. When we shine light, what happens is that you have something like what the electrical engineers like to say, a source of current, because light is being converted into current, okay? So even in the dark, even in the reverse voltage, you have current passing by. This current is coming from the conversion of light into electricity, okay? And it is a diode, so as I pass 0 and go to positive, then suddenly the energy goes, the current grows very rapidly. But actually, this is the only part which is really generating power, okay? Light is being converted. So if you remember physics 3, electricity, how can I calculate the power? Is current versus voltage. So basically, the area here is the amount of power that I'm extracting from this device. And of course, the better is this, what is called fill factor. The more close to a real rectangular, the highest the power you are achieving. So any guy who works with solar cells, he looks a lot at how nice this is, as close as possible to a rectangular shape. And as you can see here, I am making several measurements. I'm making measurements one after the other. And as you can see, the first measurement is this red, and the fourth measurement is this blue. And what is happening? I'm losing area. Each time I make a new measurement, I'm losing area, which means my cell is degrading. My cell is losing its conversion power, okay? But more than that, what is more intriguing in this material is that depending on how I do the measurement, if I'm going from low voltage to higher voltage, or from higher voltage to lower voltage, I don't get exactly the same curve. So that's why we talk about what is called hysteresis, because it depends. Just like hysteresis in ferromagnetism, if I go from and I go back, I don't get exactly the same. So I have an hysteresis. But look here. I just changed one little layer. all is equal, but I changed the compact TiO2 to niobium oxide. And then suddenly, I make one measurement, 20 measurements, and I basically don't see anything. And it doesn't matter if I'm going up or down. The hysteresis disappeared. So I don't have hysteresis, and I don't have degradation, just by changing one little layer. If I go into a little bit more details, of course, I'm not going to talk too much, but you can see here not everyone from 1 to the 9th, and you don't see any change. And actually, typically, these are the parameters used by the solar cell community, the VOC, the voltage at open circuit, the currents in how we call it, short circuit. And here's the efficiency. So our cells are not 20% efficient, so okay, they are 11%. And this is the fill factor, is how close they are to this rectangular shape. This is the fill factor. But it's clear that it's much better than with TiO2, okay? So why? That's the question. And our answer is that what we did is basically what is called band gap engineering, which is well known for the semiconductor community. So by making this, by putting another material very close to TiO2, but TiO2 is the one which is extracting first the electrons, okay? The mesoporous part, these nanoparticles are close to the perovskite. So the perovskite, when the electron makes its first transfer out of the perovskite, it goes to TiO2. And then it has the niobium oxide layer and then the metal, the semi-transparent metal. So the electron transferred to here, and then it's transferred to here, and then to here. So it's like a little ladder. While when I have TiO2 as compact and mesoporous, I don't have anymore no step for the electron. So the electrons can stay in the mesoporous part. So they are transferred, but some of them don't go to the contact. They just keep there on the mesoporous part. And because of that, this electron is very reactive. So it reacts with the organic part of the perovskite, that methylammonium, and it degrades the organic part, so that's why it degrades. And at the same time, electrons in this structure, it's like a capacitor. So if I'm keeping charge here, it works as any charge. So I have like a virtual capacitor that is changing with time. So that's why I have hysteresis. So if I go from low to high and high to low, I have changes in the distribution of charge. So I solved two problems with just one simple change in this layer. Okay? So since time is running up, well, of course, that as a material scientist, we have to do a lot of experiments. So we did what were the effect, for example, of different thicknesses, how this influences. I'm not going into too much of detail, but there is a clear dependence. So this result I told you was for an optimized thicknesses. So if I have a very thick niobium layer, I do see hysteresis. This is a way of measuring hysteresis. So I do have hysteresis. And the same effect is seen in the TiO2. So we have to optimize. And it depends on the deposition method. I told you that I had two ways of producing the perovskite layer. One, what is called one step and two steps. In one step, I just drop everything together, spin coat, and the material is ready. The other, I put PBI, and then the organic, and then the inorganic part, and then I produce. And this has effect also in the performance. Again, I believe I'll go a little bit fast. I'm sorry about that. The only thing that I want to go into a little bit more detail is exploring a little bit the composition of the niobium oxide. One nice thing about working with ceramics is that you can dope, you can change the electrical properties just by changing the composition. So that's what we did. We changed the amount of oxygen inside the chamber during the reaction. Okay? And as you can see, you can have dramatic change that you can see with your eyes. So if I put too little amount of oxygen, 3 SCCM, the material becomes black because I'm not producing any more niobium pentoxide, but niobium oxide or niobium double oxide, NBO2. Okay? So we did explore this, and again, not trying to be, I know that this is already too much information, but as you can see, we can follow the optical properties is the transmittance with wavelengths, and you can see clearly that with very little oxygen, the material is completely different. It's another material. And there is an optimal concentration of oxygen, where there is a little bit of deficiency of oxygen, so you have oxygen vacancies that are good for the electrical conduction. So here I'm looking at the conductivity against oxygen flow, and as you can see clearly, there's a dramatic drop and then a little rise. There is one best concentration where I have the maximum conductivity, or the minimum conductivity. The maximum conductivity, the minimum resistivity. Okay? And the point is that what I want is that this is this is an electrical material. Okay, so it's participating in a circuit. So I want to minimize any loss of resistivity of anything else. Okay. So again, not going into too much details, but I just want to conclude that we can oxygen flux strongly affects, and that I can have an ideal material with 3.5 S sensitivity. If you are interested in not reading the articles but seeing the lab, we published this work in this JOV, Journal of Open Visualization, so you can actually see the people, not me. I am the guy who only tries to fund this. And actually, this work of us has attracted the attention of CECEM Brasil and Petrobras. So CECEM Brasil is a Swiss company which is producing solar cells in Brazil. So as I told you, nowadays, 90% of the market is silicon and it's produced in China. So if you want to have a chance to compete, we have to go to other alternative materials. Perovskite is one of these alternative materials. So CECEM Brazil got interested, and Petrobras were just about to sign a project with Petrobras and try to develop. Just to finish up, and since I think it's a nice opportunity, I don't just work with solar cells. The other big theme that I work is with bioelectronics, and one of the materials that I work is with melanins for bioelectronics, and melanin is the material that we have in our hair, in our skin, even in our head. And what is interesting about it is that it is a semiconductor. And I'm taking the patience of you just to give one of the ideas. So we have just published 2 weeks ago the use of this melanin as a sensor for pH. And it's working very, very nicely from a very simple synthesis that we discovered about 15, 20 years ago when I was still in the University of São Paulo in Ribeirão Preto. And we have made a very, very nice pH sensor. The other thing that we are developing is for, if you want to go to bioelectronics, you have to have electronics that are like this, that can be put in your skin, that are flexible, okay? So what we are trying to make is use natural rubber latex as a conductor, so we are combining with P.PSS, and you can see that we can change the resistivity quite a lot by doing the appropriate mix. Again, and this is the actual device, so we can stretch. You know that latex is the best elastomer on Earth, so you can stretch, and you can still keep this material conducting, but actually it can be even be used as a sensor of movement if you want. Okay? But again, I know that it's too much. So this is my research group there. So there I don't use ties, I don't use this. I am using my vice president hat. But as a researcher, this is the group. And I just like to point out, so the Sylvia is the one which is a specialist in perovskite solar cells. She's actually working in CECEM Brazil at this moment. She's part-time in Bauru, part-time in Belo Horizonte. This guy is also doing a PhD on this subject, but we have Miguel, who is in a couple of months going to Cambridge, work on bioelectronics, and these are other students there. And the melanin guy just came from Swansea in England, where he developed his part of his PhD. And Juliana is the latex girl, so she did her PhD on this. And by the way, I think it's quite interesting to tell, she's a biologist, she's a chemist, this is a physicist, so my group always is multidisciplinary. We use a lot of people from different things. So as I told you, many people are responsible for the work. I'd like to thank you, but for those who have just started, and congratulations in starting the graduate program here in UNESP. UNESP is not only here in São Paulo, actually it is in 24 different cities, and we have big numbers on research. We are very strong. One of them is exactly here. I would say one of the best is here, theoretical physics. But we are strong also in material science, biotechnology, and other fields. And just to finish up, this should be my new lab that is just about to be finished. And I hope that in a few months, I will start putting the solar cell program there with Petrobras, the help of Petrobras. So thank you very much for your attention. And again, I'm very honored and pleased to give this first aula magna here in IFT.
So we have time for questions.
So first, thank you for the talk. And if I'm recalling right, there is a theoretical maximum limit for the solar cell's efficiency. Is the perovskite cells close to it, or?
Oh, yeah, I don't need a mic. I have the mic. It's quite close because the question is, you have a maximum possibility, and I just told about one material. Because you saw that from that first graph, there was solar cell that achieved 45%. How do they achieve 45%? Because actually it's not one material. It's like a lot of layers of different materials with different band gaps, all optimized to have the maximum absorption of light. Because remember this, the sun is emitting from the infrared to the UV. So, and you have a gap. So you can only absorb energy that is equal or higher than this gap. So if I have only one junction, the maximum that I can achieve, more or less, theoretically, it's 27%, if I'm not wrong. And there is an ideal gap that is optimized this, okay? And we are achieving 24, 24, 23, 24%. So it's very close to the maximum theoretical conversion efficiency. Actually, sometimes there is some controversy on saying that, for example, just to give you a little bit of the discussion, because this is thinking that I can only produce one electron for each photon that is being absorbed. But of course, you can think about other processes, secondary processes, or for example, if I come with a lot of energy, this would lose energy very rapidly, and one of the mechanisms of losing energy is producing another excitation. If you don't consider more exotic, let's say, improbable, 27% is more or less the limit, okay? But there are people calculating that maybe it's, if you had some special material where this secondary production of excitons would be available, the theoretical limits could be a little bit higher, okay?
More questions?
So it is not clear to me that there is a trivial link between being renewable and being good for 3 reasons. First being, we have to agree that what's bad is that our non-renewable sources are bad for the environment, and not they are finite. And the second being, we could, in principle, harvest the energy from the sun to destroy the Earth with an evil beam. And in particular, solar panels are known for incinerating accidentally birds and bird life, etc. So how can we measure how good for the in some
no, that's a very nice question, because I didn't go into too much of the details of the technology. There are basically 2 wide differences in technology. So there are these that are these big panels, and basically the idea is that the sun is directly converting by this light that is achieving this panel. But there is another technology, this is maybe the one that you are talking about, the birds, that you can have concentrators. So instead of doing a big panel, you do a small cell like this, but you put a big lens, and then the lens is concentrated in this small area, but this small area uses one of these high efficiency cells. Yeah. So you can use the 46%, let's say, but in a concentrate. Then the cost will be diluted by the amount of energy. Okay, so there is a lot of people just concerned about the economics and let's say the sustainability of all the process. Because of course, you use energy to produce the cells. First point. Okay. So there is a lot of calculation saying, but how much time is needed for this cell to work to at least cover the amount of energy that it needed to produce it? And typically, depending on the place, of course, but typically in a few months, depending on the technology, this is already done. The big question with perovskites, as you have observed, it uses lead. And lead is very toxic. Okay? Silicon is no problem. Silicon is silicon oxide. Everybody knows when you go to the beach, it's basically sand. So you don't have to be concerned about silicon. But with lead, you have to be concerned. So there are, of course, a lot of people concerned about all these questions. Sustainability, how can we get rid of these materials when they don't work anymore. And then you can do a lot of calculation. This is actually being done, okay? So I can tell you that solar cells are very much green in the sense that they are not just a question of that they are substituting CO2, but they are not doing too much harmful stuff in the environment, okay? But there are people that are much better than me too, and I can send you a review if you are interested.
I'd like. Thanks.
Welcome.
More questions? Actually, I have a question. So degradation is really the big issue with the perovskites. So can you say something about what is the typical lifetime of a perovskite solar cell that people can get?
Yeah.
And also, because I was under the impression that humidity was really the big issue to degrade it. So can you talk a little bit also about that?
Yeah. Typically, if we live in the environment without no kind of protection, this cell will last maybe 2, 3 days, 4 days. And there are many photoreactions that involve humidity in water. CSAIN is developing a technology, and this girl, Sylvia, working there. They produce all with no vacuum, no special environment, anything else, and the cells are staying quite well for at least 40 days. Okay, so this is one of the questions. So, if you have some kind of photoreaction, you have to find a way to protect the cell from the environment. But this is actually a question that was already more or less quite well solved by the organic photovoltaics community, because the organic materials are also quite unstable. So they develop many nice ways to basically seal very well the cell, and then you don't have the influence of water or anything else, okay? So it depends a lot on the technology you are using to seal and stuff like that. We believe that, like in organic photovoltaics, that these cells can easily last for, let's say, a couple of years, at least 4 or 5 years, which would sound okay for many applications, but not for photovoltaics. If you go to a store and you buy a solar cell, typically, they will give you 20 to 30 years guarantee. So they say, this cell will work for 20, 30 years. So to really become competitive, we'll have to go to this level of stability. And this is quite a challenge. This is basically what this community is working a lot on these days, trying to change. For example, there are now some formulations that have no organic parts, because the organic parts are known to be unstable, all these molecules and things like that, they tend to react with time. So it's one of the big challenges. But actually, as apparently, there are already some people trying to put it in the market. So maybe in 2 or 3 years, there will be something in the market with the perovskite.
Related question. Is there any organic photovoltaic cell that is lasting 30 years that already? Did they manage?
That's the problem. The organic photovoltaics, I can look there, but it started being really seriously nice with efficiencies of 5% in the last 15 years, more or less. So we still don't have no cell that started here and persisted for 30 years. But what one does are accelerated degradation techniques, try to simulate. Oh, I'm doing something for 1 month that's equivalent to 1 year. And so by this accelerated degradation, I can estimate that it will last 30 years, but it's always an estimation.
Is research with niobium more active in Brazil than in other countries, or is it just a coincidence that
the niobium?
Yeah.
Actually, we have a lot of the mineral. The mineral is easy to extract here. It doesn't mean that it doesn't have niobium in other places, but it's easy to extract.
What I'm asking is the scientific research on niobium more active in Brazil, or is scientific research, are people studying all over the world?
I'll take the opportunity to talk a little bit about this CBMM. They invest quite a lot of money in research because their main market nowadays is basically on metallurgy. So it's used in magnets and stuff like this, and this alloy. So there is one guy, which is a PhD guy, very well, very good research, and he works day and night, his whole week, just looking at patents and looking at papers all around the world that has the name niobium. And as soon as he finds something that is interesting, he goes there and talks to the guy. So in our case, they are going to invest in not in us, but in CSAIN, about 1 million reais, and there is no call, nothing like that. He just, I know that you are working with the solar, so let me see how they are they good, blah, blah. And then they go there, oh, how much do you need? 1 million, here it is. Don't have to write project, don't have to write anything. They just give me back the results. I'm just interested in the results. You have to do, of course, of course. But actually, they are going to put in the market some batteries based on niobium that the Japanese developed. So they are looking all around the world. They are not interested, I'm just going to invest in Brazil. They are investing in Japan, and they are going to put in the market one new battery with niobium as one of the main components, which is, as they say, makes the batteries much better in the sense of accumulating charge and stability. So they are looking all around the world.
Just a comment that some of the best coils for superconducting magnets, they're based on niobium, so there's a huge market for that.
Yeah.
Even the LHC uses niobium.
Hi, thank you very much. Very nice talk. So in terms of efficiency, and I know, correct me if I'm wrong, I think silicon-based solar cells, they must have silicon. It's usually very pure, very crystalline, right?
Yeah.
And as you mentioned, for perovskites, and I know also CIGS, they can be like very polycrystalline.
Yeah.
What is the fundamental difference between these two cases?
Well, that's a very nice question. The problem with silicon, let's start with silicon, is that it's fundamentally not so nice for this kind of application in principle because of the indirect gap. So you already have some problems that you lose a lot of light coming. So you cannot do as thin as we are working with. You can't do 200 nanometers because it will basically become transparent or semi-transparent, and you lose a lot of light. So you have to have it thicker. So you need thicker materials for silicon to start. Then the second point is that to make this separation of charges is not so obvious. And one of the main problems with materials like silicon is that if you don't have a perfect crystal, you have a lot of defects. And these defects will be responsible for what we call recombination. The charge won't reach the contact. It will basically recombine inside the silicon itself. So the more perfect you have, the less is the probability that you have this recombination. Then the efficiency will go up because these electrons will somehow reach the contacts. Okay? And the other thing is that with silicon, the trick to make the charge separation is by this internal electrical field. And this is quite okay, but sometimes not so good. So you have a lot of drift diffusion. So again, I have to have a very perfect material to be sure that these charges that are photogenerated, they will not find another pair and have a recombination, and then I lose the excitation I just created. So the perfect, the best. In the case of perovskite or CGS and even the polymer or organic materials, is that normally this separation is much more efficient, and you use these heterostructures to do this. Nobody knows in too much detail. So this is the nice physics that people are looking when they look at device. Why since I created, they are generating the same place, why should a positive and a negative charge separate and not just recombine? They will be bind and then recombine. Why do they separate? So apparently in these materials, what happens is that since you are using heterostructures, so you have interfaces that will somehow attract the charges to one or the other side, and you don't have the defects, or at least the defects are not as active as in silicon. So this is another big question. What are the defects doing in perovskite? There are defects, for sure, but apparently they are not electrically active. So why? This is another, so there are a lot of questions. We made it, it works, but the physics behind it, there is a lot of questions. This is what we are pursuing, so that's why we have all this. We are physicists, we are not engineers, we are looking to try to understand all the physics behind, but it's a nice...
Thank you for your talk, very interesting. And I think that it was last month, Europe and USA launched the Solar Orbiter. And I don't know if the kinds of cells are the same material as used on Earth, or they're going to test some new kinds of solar cells.
Yeah. No, this is very nice. That's the point. When you are sending something to the space, the cost is more of the cost of sending than the real cost of the thing. So these record cells, these 40%, are the ones that typically go to space. Because there you want the maximum efficiency and you are not caring too much if it's going to cost $1,000 or $10,000, as long as they produce, you need less mass, you need less weight to produce the same amount of energy.
But the efficiency is higher?
It's very, very much high. So typically, these solar cells that are sent, like Orbiter and something else, they are on the above 30, 40%, typically. They are the best cells you can get. And that's why there is a lot of interest in this multi-junction, because economically, for someone to buy, it makes no sense. It's too expensive, but send it to space, if it's going to be half the weight of another cell, because if I'm sending 10%, but it's 40%, I can save 4 times the weight in this very simple calculation. But there are other, in fact, there are other things into consideration, because when you are in deep space, there is a lot of high energy particles coming in, so they must be much more robust to degradation due to high energy particles. And these materials are typically much more robust. They don't degrade so easily with the radiation. Normally, I'm not so sure if they're classified, because the thing is that NREL is this based in the US, and it wants to keep the records and to be sure that these records are valid. So you have to send to some kind of metrology to be sure. When I'm putting this graph there, it's not that I measured it. I have to have some metrology, and NRL is responsible for that. So I don't believe that they are so much interested in keeping this so secret. Because actually, normally the difficulty in doing these high efficiency cells is little tricks that only the guy that does it knows it. Even though I can know exactly the composition, to reproduce, it's very, very hard. As I told you, I was in Berlin in the week that Helmut Zentrum Berlin was making the record for a tandem cell, silicon perovskite, 29%. And I visited the facilities. So they have basically everything you can dream of in terms of this is just for this is just for that. You have all these protocols for putting the material here, the material is of the best quality. Blah. So to achieve such high efficiencies, you have to be very careful in each step. So you don't have to care too much. You have to be careful that nobody gets into your lab and learn the tricks. But if you know the trick, it's not easy to reproduce. It's not easy to reproduce. It's not easy. It's know-how.
I have another question about your solar cells. So you create this solar cell with a niobium oxide, but you still keep a layer of titanium oxide. Is that really because of this step process, or is there another reason why you still need a TiO2 layer?
Yeah, in principle, since we believe in this, let's say, band gap engineering, TiO2 should be important. But CSAIN, for example, the factory, is more interested in processes that are simpler. And putting this mesoporous layer is a step which is not very nice from the point of view of the industry, because you have to put kind of like a paste, like you are painting the wall. You have to paint, and afterwards you have to do some heating to get rid of the organic part, because there is it's a paste, so it has an organic part and the inorganic to get rid of. So this costs time and can be not reproducible. So they are trying to make a pure niobium without the titanium oxide. So we have some experience with that. I didn't show because this is basically from CSAIN, but it works also. TiO2 is not fundamental. So niobium can be used alone in other structures.
Any further questions? So if not, let's thank the speaker again, and I welcome you. Refreshments upstairs, coffee and cake, and yeah.